last lecture towards the end, I just introduced a new topic in power electronics, that is DC to DC power conversion. Okay. This topic, or DC to DC power conversion, is very popular in SMPS, switched mode power conversion or power supplies. Okay. Because the moment someone says DC to DC converter, first thing that comes to my mind is switch mode power supplies, and maybe second application could be in drives, okay, a chopper fed DC motor. Okay. Why are they so popular? Because why DC to DC conversion is so popular in switch mode power supplies? I am sure you all know, maybe in early 90s, around 1991, 20 megahertz PC80 was the state of the art PC, okay, 20 megahertz. 10 years down the line, we have PCs, Pentiums operating in gigahertz. Okay. As the frequency range has increased, what happened to the biasing voltages which are required inside? In our lab, we just, all the TTL circuits are being biased using a 5 volt supply. As the frequency has increased, the trend or the trend is to use power supplies of lower voltages, okay, because of various reasons. I told you that when the device is being switched at a very high frequency, in order to reduce the losses, I have to reduce the supply voltage. Same concept is true even in the power supplies, or even in, for that matter, even in computers. After all, there are ICs, they have to be switched at a very high speed or at a very high frequency. So there is a 3.3 volts DSP, digital signal processor. Now it is being used in drives. And I was told that 2-3 years down the line, the requirement for a power supply is, or the power supply rating that is required is 0.5 volts, 100 amperes. I will repeat, 2-3 years down the line, power supply that are required in computers or in VLSI design is 0.5 volts, 100 amperes. See, in the sense, for an electrical engineer, if there is a short circuit, voltage is of the order of 0.5 volts maybe. Now, I do not know how to generate a VREF for a supply voltage which is as low as 0.5 volts, how to protect it against overload or how to protect against short circuit, because the rated voltage itself is 5 volts, current that is flowing is of the order of 100 amperes. See the challenges that are ahead in DC to DC power conversion. Application requires very stringent specifications, 0.5 volts, it should be maintained constant. Ripple, again there is a limitation on the ripple, or a change in output voltages is again very small. The challenges in DC to DC power conversion are tremendous. Okay. Let us see, before going into the switch mode power techniques, what is the power supply that we are using in our labs, or you have been asked to design a circuit which requires a power supply, and your teacher has told design or make use of your own power supply, do not use the power supply which is available in the lab. What sort of a power supply you would design? Okay. That is nothing but a linear regulated power supply. What is the circuit? Circuit is very popular and very simple. If I want to have a 5 volts power supply, I will use a step down transformer, maybe 7 volts 707 transformer, I will rectify it using 2 diodes, full wave rectification. I will filter it using a capacitor. Then I will use a series element. What sort of a series element we will see sometime later. And out here at the output, I will get a regulated power supply. Okay. 230 volts input. This transformer secondary winding depends on the voltage requirement at this point. Okay. So what happens the moment I use this sort of a configuration? Okay, this is nothing but maybe AC to DC conversion. I have discussed almost all the circuits in AC to DC conversion. Somehow this part I have not discussed. I had in mind that I have to teach this, and I have postponed it now. Okay. So what happens here? How does the source current look like? If there is no capacitor here, at this point Vu looks like a full wave, or Vu is a full wave rectified version of the input wave. I connected a relatively large capacitor here. I told you that filtering requirement in a 2-pulse converter is much more compared to 6-pulse converter, because though I am calling it as an unregulated, voltage at this point should remain approximately constant. Okay. Unregulated because if the input changes, at this point also voltage changes and does vary. There is in other words, there is a significant ripple in the output voltage. So at steady state, depending upon the current that is flowing out of this terminal, capacitor voltage varies in this band. Okay. The cathode potential is nothing but Vu, anode is a sinusoid. Okay. I told you that Vu remains approximately constant. Diode cannot conduct till anode potential is higher than the cathode potential. So if this is the variation in Vu, okay, and this is the dotted line is the anode potential, at this point cathode potential is equal to the anode potential. So diode starts conducting. When diode starts conducting, one of the diodes, the positive of here and negative of this diode, when diode starts conducting, input voltage is same as the output voltage. Okay. It follows the sine wave. Okay. Somewhere at this point, input starts decreasing. Now capacitor voltage cannot change instantaneously. Load current is also very small, or it depends on load application or the time constant of the circuit. It depends. The capacitor voltage variation here depends on the time constant of the circuit. So this is the fashion. Capacitor voltage falls approximately linearly. Changes not much. So till here, in the next cycle, source does not supply any power. Okay. Diodes are reverse biased. At this instant, diodes are forward biased, source starts supplying current. And what is the current at this point? KCL has to hold good, Kirchhoff's current law has to hold good. So this current should be equal to the capacitor current and the load current. In other words, C dVu by dt, the capacitor current, plus the load current should be equal to the source current. Okay. By the way, can I differentiate this point? There is a discontinuity here. Can I differentiate it? There is a discontinuity, C dV by dt. I have to differentiate this function. You find out an answer to this question. Okay. So if you observe the source current waveform on the oscilloscope, there is a very peak current here, a high current starts flowing here, I am neglecting the inductance. If there is no inductance, large current will flow and it slowly dies down. At this point current becomes 0. So, there is a sharp pulse of current here, and after pi in the negative of this diode, through this diode, a sharp pulse of current for a very short duration. So, in the linear regulated power supply, if I use this sort of a configuration, and let me tell you, invariably you use the same configuration. Source supplies power for a very short duration, okay. And if I draw, or if I find out the harmonic spectrum of this waveform using a Fourier series, it has a predominant third harmonic component, apart from the fundamental, okay. Harmonic content is very high, source supplies a peaky current, okay. So, what is the other reasons? So, in order to get a regulated power supply, we use a series regulator. Maybe in the lab you might have seen, or you might have used this regulated power supply chip, a 3-legged chip, tip series, okay. Input is a 5 volt 7805, output is 5 volts regulated, input is the unregulated. The third pin, the center point pin, is the ground, input and output, okay. It is mounted on a heat sink. This is the heat sink, and this is a regulator, series regulator, which you might have used in the lab, okay. Now, here is the circuit: unregulated, series element, regulated, okay. Regulated is supposed to remain constant, okay. I said 7805, I see if I use here, output voltage is maintained at 5, and unregulated should be a minimum of 7.5 volts and a maximum of 35 volts. So, if you see the specifications of 7805, you mean unregulated minimum is 7805, regulator is 7.5, only then you will get a 5 volt regulated supply, and output could, and the maximum value could be as high as 35. Till 35 you will get a regulated voltage of 5 volts. Now, what happens to the difference in these two voltages? If it is 7.5, output is 5. If the input is even 35, output is 5. Where does the remaining voltage goes? Answer is very simple. The remaining voltage is dropped across the device. Okay. So, what is the power loss? Power loss is voltage across the device and the current flowing through it. Therefore, so as unregulated voltage increases or changes, power loss that is taking place in the series regulator also increases. Okay. Why am I using the term linear power supply? That is because the series element that is used is operated in the linear region. Almost in power electronics, the switches that are used, either they are operated in cutoff, that's current flowing through is 0 theoretically, ideally, or in saturation, when the voltage across the device is very small. We seldom operate the device in linear region. We may operate in a quasi saturation. In other words, the saturation just begins to start. Okay, definitely not on linear. In power electronic circuits, all the devices are operated either in cutoff and in saturation. So 7805, the regulator chip that you are using in the lab to get a regulated power supply of 5 volts or -5 or +8, -8, +12, -12, you operate them in linear region. That is why they get very hot, because power loss that is occurring in the device is voltage across it, which is difference between unregulated and the regulated, and the current flowing through it. Okay. See, you might have seen this box, a regulated power supply in the lab. Okay. 30 volts, 2.5 amperes, very common. Okay. Why it is so heavy? Why it is so heavy? I don't think the computer, the Pentium 4, I don't think is as heavy as this. Wattage here is of the order of 150 watts. 150 watts, 150 watt power supply. I'm really finding it difficult to carry. It's heavy. Why it is so heavy? And you might have seen why this is a heat sink. Why there is such a big heat sink, and all the devices, these are the devices, the series elements or regulators are mounted outside. Why? You don't find them in a computer. Computer also requires a power supply. Let me tell you one thing, computer power supply requirement may be much higher than this, and I can still hold it in my palm. The Pentium 4 power supply, okay, the requirement is higher than this, wattage is higher than this, still I can carry in my palm, and I don't find such a big heat sink and all the devices there. This is there, so heavy. Why? Because these elements are operated in linear region. So if the input is fluctuating, output has to remain constant. If it increases, power loss increases, that heat has to be dissipated. That is why they are mounted outside. Okay, so that is about linear power. Okay. So the disadvantages of the regulator linear power supplies that are available in the lab, or which you design it for your circuits. One is efficiency is very low. Efficiency is very low because series regulator is operating in the active region. Okay. So power loss is high. If the power loss is high, temperature rise is high. So I need to use a bigger heat sink. Heat sink requirement increases. I said filtering requirement is also high because single phase, to maintain a approximately constant voltage, I need to use a larger capacitor. So overall size of the power supply increases. Source current is peaky, predominant component is third, okay, it's difficult to filter. And finally, it's the most important, we require a step down transformer which is operated at 50 hertz. In other words, I require a 50 hertz transformer, a step down transformer. That is why the overall size of the power supply becomes big and bulky. Okay. Why am I saying a 50 hertz transformer? What is being done in SMPS, in switch mode power conversion? Let us see, we will discuss. The frequency of operation in SMPS is very high. Minimum could be of the order of 100 kilohertz. And all the magnetics, inductor or a transformer that is being used are operated at this frequency, mind you. Okay. Now you may say that DC to DC, how did you get DC from, or where did you get this DC from? After all, the supply that is available is AC. Okay. So do I need to have a 50 hertz transformer there? So if I use a 50 hertz transformer, the purpose is lost. somehow I have to do away with this 50 hertz transformer. Okay. Let us see, as of now you assume that DC is available. How to get this DC without 50 hertz? I will come to that point sometime later. Okay. So, this switch mode power supplies or DC to DC converters are operated at a very high frequency. All the magnetics, they are operated at this frequency. These SMPSs are broadly classified into two types. One is without transformer and second one is with transformer. Now immediately you may say, DC to DC, how can you use a transformer? Our machine teacher has told us that if you connect a transformer to a DC supply, it will get damaged, or there will be a short circuit and transformer gets damaged. I am not saying that what your teacher has told you is wrong, is correct. But I am also using a transformer in a DC to DC power conversion. What exactly, what is the difference in operation, we will see sometime later. Okay. As of now, assume that transformer can be used in DC to DC, and they are being used. Okay. See, a very popular equation, VA, a volt ampere rating of a transformer is approximately given by 4.44 into F into phi into N. This is voltage induced in the windings. N1, if it is N1, it is in the primary, if it is N2, it is the secondary, okay, into the current. Okay. Now if you see in this, for a given VA rating, as F increases, N comes down. Okay. N comes down. If N is nothing but the copper, N is nothing but number of turns. If I reduce the number of turns, the copper that is used in the transformer also comes down, so weight comes down. But then you may say, the moment I switching at a very high frequency at F increases, core loss increases. I am not saying that, I am not disputing that fact, core loss do increase. But then I can't use the so called CRGO core or CRGO laminations in a transformer. Okay. Laminations or 50 hertz transformer core material cannot be used for a high frequency transformer. There are special materials like a ferrite core. Okay. This is a ferrite core. So here if you see, this is a ferrite core lamination for a core for a ferrite transformer. Okay, made up of this material is of ferrite. I can use it for an inductor or I can use it for a transformer. It's very brittle, so laminations, you cannot make a thin laminations out of it. Okay. So what is the average flux density in this core? Is again is low, is of the order of maybe 0.2 to 0.25. Designer will take of the order of 0.2 to 0.5. Okay. There are other core, high frequency cores are available like amorphous alloy. B average is of the order of 1 to 1.1 Tesla. Okay. So as you increase the frequency, you have to go in for other type of cores. That's the reason, I hope all of you know why all the communication equipments or communication people operate at a very high frequency in terms of gigahertz. Answer is very simple. As your operating frequency increases, all the magnetic size comes down. The transformer size also comes down. Okay, weight comes down. Okay. Yes, core losses, there are other, you can take care of it by using other material. Now the first one in switch mode power conversion or DC to DC conversion is the buck converter. Okay, a buck converter. A buck input is DC. Okay, output is available at this point. I am assuming that a resistive load is connected at the output, okay, or C is the filter capacitor, sorry, CF, it should be CF is the filter capacitor, LF is the filter inductor, LF is a filter inductor, D is a freewheeling diode, okay, freewheeling diode, S is a switch, S is a switch. What sort of a switch? Can I use a SCR in this circuit? My question is, can I use an SCR in the switch, in this circuit? Answer is both yes or no, yes and no. Why yes? In principle you can use. Is a control switch, I will apply a gate signal, it will turn on and I have to turn it off using some other means. We did use SCRs in AC to DC conversion, where there is only one pulse per half a cycle, or line commutated converters. Why did we use there? We used there because turn off was relatively easier in a single phase bridge. Recall, if I trigger T3 in beyond pi, okay, immediately it applies a negative voltage across T1 and T1 turns off, okay. But then we saw in pulse PWM converter, we wanted to switch a large number of times in the positive half cycle itself. We did not use their SCRs. I said I'll use only switches here, and I told you that you need to use the self commutating devices, or the devices which are capable of turning off using gate. If I use a SCR, I have to use a separate source and some other elements to turn it off, because I can turn it off only by applying a reverse voltage across the thyristor, okay. I can turn off a conducting thyristor by applying a negative voltage across it, some sort of a forcibly I have to turn it off, or force commutation techniques should be used, and there are techniques available. And in the present day, with the technology that is available, using SCRs and using a force commutation technique doesn't make sense, okay. It doesn't make sense. Using SCRs only in line commutated converters makes sense. They are still popular there, okay. For example, that's what even in HVDC power transmission, I told you that both sides there is AC, okay, AC to DC, again DC to AC, both sides AC is available and SCRs are still being used there, they are popular there. Definitely not in DC to DC power conversion, wherein you have to use some other technique to put off the thyristor or turn off the thyristor. So the S here is a self-commutating switch, okay. If the power level is low, you use a MOSFET, okay. Invariably if someone says SMPS, the device that is used is, the first thing that comes to my mind is a MOS. It could be a very safe assumption, okay. It could be a MOS, and it is a very fast device, So, and all these inductors switched at, because S is switched at a very high frequency, magnetics are operated at that frequency, okay. See a ferrite inductor, okay, is made up of the same material, maybe a smaller core, ferrite core, okay, and see the leads. Why there are more than one conductor twisted together? See, I am trying to untwist it. See, there are more than one conductor. There may be around six thin straps of conductors twisted together make one conductor. Why not use, definitely the copper wire of single strand of this cross sectional area is available, copper conductor thicker than this is also available. Why did the student who was using it in the lab used 6 thin conductors, wind them together, of course it's a difficult task, and made an inductor? Okay. The answer is, if I were to use a single conductor, the quality factor of the inductor would have been very low. In other words, the resistance, the internal resistance of this inductor using one conductor is much higher compared to the inductor which is made up of large number of conductors. This is also known as something known as a Leeds wire. Leeds, LIT is a Leeds wire. Okay. Using a Leeds wire, if you use an inductor, this has the properties are almost similar to that of an ideal inductor. Okay. Ideal inductor. Q is very high, quality factor is very high. It implies that R, internal R is very small. Okay. Internal R is very small. Okay. So while during analysis we will neglect the internal resistance R, all the elements are ideal. When the diode is conducting, voltage across it is 0, same assumption that we made in AC to DC conversion. V naught is assumed to be constant. Okay. Now you may say capacitor is supplying power, so it should discharge. Yes, it will discharge. The one V naught will change, but what is the variation V naught? It's very small. Maybe sometime tomorrow I will give you the specifications that are generally mentioned at the output. Okay. So close the switch is turned on or off at a very high frequency. So S is on for a D into T seconds, where D is a duty cycle, and it is off for 1 minus D times T, where T is the time period. So switch is on for dt seconds and it is off for 1 minus D to T seconds, where D is a duty cycle which is equal to T on divided by T on plus T off. Okay. And T on plus T off is nothing but the total time period T. So what are the equivalent circuits during these modes, when the switch is on and when the switch is off? How does the circuit work? Let me tell you one thing, working of DC to DC converters is relatively easier to understand, because input is DC, output is also DC, time invariant, and there are few passive elements here and there. Okay, it's relatively easier to understand compared to AC to DC. In AC to DC, input itself is pulsating. Like our circuit course, DC circuits are easier to solve compared to AC circuits. Okay, so let me tell you one thing. If you have understood AC to DC circuit operation or working of those circuits, this is going to be relatively easier. Okay. So that note I will start the working of explaining the working of a buck converter. See in this circuit, when S is closed, the source voltage is applied across D in the reverse fashion. Okay. So positive to the cathode, negative to the anode. So diode is reverse biased. Okay. S is closed and it is closed and is switched at a very high frequency. Okay. We assume that V naught is constant. Okay. At that instant, even though VDC is unregulated, we assume that VDC is also held constant at that time, remains constant. a positive voltage if is a buck converter, V naught is less than VDC, I am saying buck converter, V naught is less than VDC. So voltage across the inductor is VDC minus V naught. At this point it is V naught and at this point it is VDC. Okay. So equivalent circuit is a switch, VDC, L and output stage. After some time I am opening S. When I open S, just prior to opening S, some current was flowing through L. Current has to be continuous, so current starts flowing through the diode. So this is the path it will take. Okay, this is the path it will take. Okay. So the equivalent circuits are, see here, VDC source which is short circuited, the remaining part of the buck converter. After some time I opened S, there is open circuit here, there is an open circuit across the DC bus here, diode, this is the equivalent circuit. So voltage across the inductor is VDC minus V naught till the switch is on in this period, which is constant. Therefore di by dt is constant, it implies that IL increases linearly. IL increases linearly. What is the KCL at this point? IL is equal to capacitor current, this is the positive directional capacitor current, and I naught, this is I naught. Okay. So I naught is nothing but current flowing through R, which is given by V naught by R. Okay. IL is C dV naught by dt and V naught by R. See, here I am writing dV naught by dt. At this stage I am writing that V naught is constant. Please, both are correct, and let us see in what context I am saying this is constant, and here I am writing dV naught by dt. Okay, have some patience. What is the voltage that is appearing across the diode? So diode comes across the DC supply. So voltage across the diode is minus VDC. It is blocking. Okay. Coming to the equivalent circuit, when the switch is off, what is the voltage across the inductor? Now diode is on, this point gets connected to this point, so voltage across the inductor is minus V naught for 1 minus d into t to t. Now I am assuming that V naught is constant, so IL decreases linearly. Okay, and KCL at this node is the same thing. Okay, IL is I naught plus IC. IC is nothing but C dVc by dt. What is the voltage across the switch? What is the voltage across the switch? Now since diode is conducting, this point is also connected to this point, isn't it? So voltage across the switch is VDC itself. Source is blocking. A voltage rating of the diode, voltage rating of the switch should be, minimum should be VDC. Okay. So these are the equivalent circuits and the circuit equations. How do I determine the relationship between the output voltage and the input voltage? We have an inductor in between the output and input, both are DC. So I have only one condition, that is nothing but average voltage across the inductor should be 0. Average value should be 0 over the cycle. Okay. So I will equate it, the areas, positive area should be equal to negative area. What do I get? I will get this expression, V naught is equal to d into VDC. This is a positive voltage, this is a negative voltage, D naught. Okay. Now, what is the relationship between the current? I have same equations, okay, same equations. So, over the cycle is IL average should be equal to dV naught by dt average plus V naught average by R. I had assumed that V naught is constant. What it means is, yes, for some time capacitor is discharging and sometimes capacitor is charging. The variation in V naught over the cycle is 0 at steady state. At steady state, variation of V naught over the cycle should be 0. It charges for some time, discharges for some time, and this variation should be small. That is being that will be specified by the requirement, okay, or the customer specifies. My V naught changes in V naught for a change in load from 0 to full load should be of the order of less than 1% or so. That is the what could be less. It is given by the customer. That is the system demands. So, variation of V naught over a cycle is 0. So, that is at steady state V naught at t is equal to 0, some t is equal to 0 to t should be same. So, this is 0. In other words, at steady state average current flowing through the capacitor should be 0. Remember, at steady state average value of the current flowing through the capacitor should be 0. So, IL average or inductor average current should be equal to V naught by R, average value of the load current. Okay, this is the load current. Now, let us plot the various quantities, okay, the voltages across the switch, diode and the current. When I said current is continuous in AC to DC conversion, what did I mean? It meant that the load current is continuous. Remember, in AC to DC conversion, when I said especially line commutated converters, in line commutated converters, I said current is continuous. It is assumed that the load current. In power supplies, in DC to DC or in SMPS, when I am saying current is continuous, it implies that the inductor current is continuous. Please remember, it is the inductor current is continuous. What is the load here in buck converter? See, load here is a resistive load is connected across a capacitor, and I am saying that V naught will remain constant, approximately constant. So, as long as these terminals are, as long as this circuit is complete, I naught will continue to flow. Okay, I naught will continue to flow, and it is supposed to remain constant. Okay, please don't say that load current is continuous. No, load current is supposed to be continuous and is supposed to remain constant if the load is constant. So, when I am saying that current is continuous, it implies that the inductor current IL, this is continuous. Okay. Now, how does the variation look like? So, here S is on for D into T. So, IL is continuous during this period, D is on, okay, and again this is the second cycle. When S is on, voltage across the inductor is VDC minus V naught, which is positive. The difference VDC minus V naught is positive, so IL increases linearly. Which is, I am calling this value as I min, this as I max, increases linearly. And when I am opening the switch, voltage across the inductor is minus V naught, which is again constant. IL decreases linearly. So, at steady state, this value should be equal to this value. I min at this point, and I max, and after I max somewhere here should be the same. And this is the average value of current. This is the average value of current, which is I naught. I naught is equal to V naught by R. I naught, this should be I naught, sorry, this is I naught by V naught by R. I naught. Okay. When S is on, the inductor current is same as the switch current. Same current flows through the switch. The same current is flowing through the battery. See the equivalent circuit. When S is on, inductor current is same as the current flowing through the switch, is same as the battery or source current. So Is, which is the source current, okay, is same as IL. At DTs, switch is opened, so instantaneously source current or the device switch current becomes 0. Okay. At this point, switch is turned on at steady state. So, okay, diode should turn off at this point. Immediately I am turning on the switch here. So, this value of current immediately the switch should carry, okay, and that current will flow through the switch itself, okay, increases linearly, and at this point it is being switched off. Current instantaneously becomes 0. The moment I turn off S, D is turned on, okay, the inductor current has to be continuous. That current starts flowing through the diode D. Okay. So, this is the diode current variation. Okay. It jumps to I max, falls linearly, and at T you switch on S again. The moment S is turned on, I am assuming that D turns off. It may have its own turn off time, that is okay, it is neglected during analysis. Okay. D turns off, whatever the current that was flowing through the diode should be transferred or gets transferred to the switch, and the source supplies that current. So, this is the waveform that is appearing across, or this is the current waveform that is flowing through the diode. So, there is instantaneous jump when it is turned on, again there is a jump when it is turned, when it is turns off, So, when the switch is on, voltage across the switch is 0, and when the diode is conducting, voltage across the switch is VDC itself. I explained to you, okay, it is VDC itself. And when in this period when diode is on, in this period the switch is on, in this period, voltage across the diode is the supply voltage itself in the opposite sense, or source voltage VDC. Okay. At this point, switch is turned off, diode starts conducting, and it is 0 till the next cycle when S is turned on again. Okay. How does V naught look like? How does V naught look like? We assume that V naught, suppose V naught is remains constant, but then I had written in the equation dV naught by dt. Then after some time I told you that variation of V naught over the cycle is 0. Variation, average variation in the sense it starts charges for some time and discharges for some time. Okay. So, when does it starts charging and when does it stop charging? Okay. See the circuit here. Kirchhoff's current law has to hold good. Okay. IL should be equal to IC plus I naught, okay, IC plus I naught. So, capacitor will start charging if the inductor current is higher than the load current. I naught, which is equal to V naught by R, okay. Please, I naught is equal to V naught by R, and I am assuming that I naught is constant. See, there is, please don't get bit ambiguity here, don't get confused. I am calculating, or I am plotting the variation in the capacitor voltage, output voltage, okay. While calculating, while plotting the variation of capacitor voltage I naught, I am assuming that current remains constant, okay. So, I naught is V naught by R. Now, if V naught changes, I naught should change, but I am assuming that I naught will remain constant. Please, the variation is not much, variation is very small. So, capacitor will charge when IL current, the input current, is higher than the load current. When IL is higher than the load current I naught, the remaining current should go through the capacitor. When IL is less than the load current, capacitor should supply the difference in the current, okay. Current through the capacitor can change instantaneously. Remember, capacitor current can change instantaneously, voltage cannot change, okay. So, capacitor starts charging, or current flowing to the capacitor is positive when the inductor current is higher than the load current. See, this is the inductor current, this is the load current assumed to be constant. So, from this period, inductor current is less than the load current. So, difference should come from the capacitor. In other words, capacitor is discharging, V naught is falling, V naught is falling. At this point, both the currents are same, capacitor current is 0, inductor current starts increasing, capacitor currents also starts increasing. So, capacitor starts charging. Okay. You might have turned off the switch at this point. Okay, once you turn off the switch, current starts decreasing, but this inductor current is higher than the load current till here, okay. So, in this period, capacitor charges. So, see, capacitor charges till this period. Please do not say that capacitor starts charging at this point and stops charging at this point. No, KCL has to hold good, okay. At this point or beyond this point and after this point, inductor current is higher than the load current. So, capacitor starts charging during this interval, and after this inductor current is less than the load current, capacitor supplies current, because we assume load current to be constant, capacitor discharges, okay. More about it, we will see it in the next class. Thank you.